Friends, welcome to the 42nd lecture on Advanced Yield Design course. We are continuing to do estimate or locating shear center for curved sections. Okay. So, we are in the middle of a problem, we will do that now in this lecture. Hope you have done this. So, this was the last expression we had for V1, am I right? So, we found out V1 which is given by this equation, which is Vt by I or V1 square plus V1 cube by 3. So, that is V1 here. Now, let us try to find out V2. Okay. So, we will copy this figure again. Rub this. Okay. Now, I want to find V2. Okay. Let me cut a new strip now. Which is here at a distance x from here thickness of the strip is dx and I want the hatched area is this. Hatched area has got two components. Okay. Got two components now. So, I divide this into two components and write. Okay, I divide this into two components here. I divide this into two components here and then try to find out. Let us see how do we do it. So, now V2 is integral 0 to b, because that is the dimension we have for V2, V by I t, thickness is uniform, A y bar of t. Okay. dA is very simple. dA is the area of this small strip which is being considered, which I am hatching here. Okay. Which is T dx, there is no doubt. Ay bar has got two components. So, first let us do it for B1. So, B1 into T of R plus B1 by 2. So, I have done for this sample, I am just marking it here. Okay. I am marking it here. I have done for this sample, plus this is for 1, okay, plus Tx into R, this is for 2, that is this one, am I right? So, therefore, V2 now will become integral 0 to b V by I t B1 into T of R plus B1 by 2 plus Tx into R of T dx. Okay. So, we can simplify, apply the limits. Please check, we will get V2 as V by I T times of B1 RB plus B1 square B by 2 plus b square r by 2 this. We can simplify this. I get V2 in a simplified form as Vt by I B1 Br plus B B1 square by 2 plus B square R by 2, equation 2. Okay. So, equation 1 we had V1, equation 2 we had V2. Okay. Now, I want to find for the semicircular portion V3. We already know this equation. Let us draw this figure. We are looking for the curved portion, which is this. I will hatch it here, maybe with this color. I am looking for this portion. We already have an expression for this. Okay? If you know the angle, I can do it. So, now the elemental shear stress V by IT will be integral y dA plus theta 1 plus theta 2. Okay. Let us say we will put as Q1 plus Q2, where Q1 and Q2 are the shear of first and second pieces. Okay. So, let us do that. V by IT, we already have this equation, so I am writing it here. R cos theta into R d theta into T, am I right? Plus B1 times of T into R plus B1 by 2. This is for piece number 1 plus B T into R, this is for piece number 2. So, therefore, I can now expand this, which will become tau V by I R square cos theta d theta plus B1 R plus B1 by 2 plus B into R, which will now become V by I R square sin theta plus B1 R plus B1 by 2 plus BR. So, please understand this integral y dA is applicable only for the curved section. Okay. For the remaining section, we already have the forces with us, okay, into BR. So, V by I okay, let us mark it this way. This y dA is only for the curved section. Okay. So, we have now the value for tau, which is V by I R square sin theta plus B1 into R plus B1 by 2, let me write it here clearly, plus BR. Okay. Now, the elemental shear dV will be tau dA, which will be V by I r square sin theta plus B1 times of R plus B1 by 2 plus BR of R d theta into T. Am I right? Look at this figure. We are looking for d theta as a small segment. I will mark it here. The segment we are looking for. We know this is theta and this angle is d theta. This is a segment which is YD. Okay. So, this r theta d theta is very clear from there. So, now I can find dV as V into Tr by I, this T has now come into play here, of r square sin theta plus B1 times of r plus B1 by 2 plus Br of d theta. Now, we would like to take moment about of this force about the point O. This is the point O. Okay, take moment about this point. The force V is acting here. Okay, we will take the moment of this particular dV. Okay. So, we will say taking moment of this elemental shear about O. So, we call that as dm, which will be tau dA into r. See here, the distance will be r, is it not? Okay, into r. So, therefore, dm now will become Vt r square by I. Okay, let me write the equation for tau dA. Dm will now become Vt r square by I r square sin theta plus V1 times of r plus B1 by 2 plus Br of d theta. Integral dm will be the total moment m, which will be equal to Vt r square by I integrated from 0 to pi r square sin theta plus B1 times of r plus B1 by 2 plus Br of d theta. Equation 3. So, m will now become V r cube r square t by I r square minus cos theta plus B1 times of r plus B1 by 2 plus Br theta, applying the limits 0 to pi. Okay. I will copy this equation. So, we will do BRQ by T by I R square 1 plus 1 plus pi times of B1 R plus B1 by 2 plus BR, which now become B, this is R square, sorry, B R square T by I 2 R square plus pi times of B1 into R plus B1 by 2 plus BR, equation number 4. We have the m value now. Now, we will take moment about the point O. Take moment about point O, we get V into E should be equal to m, which is actually equal to m. Let us look at this figure and write this equation. We will copy this figure and write this equation. Okay. Selection tool. This is V3, okay, let us mark this, this is V3, curved section, okay. So, now V into E, because this was V, this is the point O, V into E, which is anticlockwise, should be equal to m, okay, minus, okay, V1 into B by 2 minus V2 into R. These are for, sorry, let us do it this way, m minus V1B twice, because I have V5 also, minus V2 into R twice. So, friends, I have equation m, see here, I have equation m, which is having the term V, right. So, m is there. We also have equation for V1. We had the equation for V1, which also has V. So, we had equation for V1. We also have equation for V2, which also has V. So, V2 also V. Of course, B and R are geometric properties. Okay. Can I find E? So, E will be, so V goes away, m by V minus 2V1B by V minus 2V2R by V. I can find it. Now, friends, in all these equations of m, V1 and V2, see here, in V1 I have I, in V2 I have I, in m also I have I, where I is the moment of inertia of the whole section. So, from first principles, you will be able to find out the moment of inertia of all the 5 parts, part number 1, part number 5, part number 2 and 4 and part number 3. I think moment of inertia is sum of second moment of area of all the pieces. You can do it for component 1 and 5, component 2 and 4 plus component 3. I will give you the equation, you please check. The moment of inertia of this whole section is given by RTQ by 6, 3 pi plus 12 times of B plus B1 by R plus 4 times of B1 square by R into 3 plus B1 by R is the moment of inertia of the whole section. You can check this, okay. So, friends, we have learnt how to do the shear center problem for curved section which has got a mixture of rectilinear and curvilinear sections. From the first principles we found out how to locate E. So, locating shear center for geometrically complicated section is not that easy, okay. We have got to gradually divide them into parts, into finite elements and keep on assembling them and do it slowly and patiently. It is not that easy. So, when you have got form dominant designs where the geometric shapes are dependent on the functional requirements, obtaining shear center to check whether unsymmetric bending will be caused, whether twisting will happen, whether stability will be checked, all will become a prerequisite. So, standard softwares cannot handle special kind of structural shapes. It is always better, friends, to use the CAD models, develop these geometric shapes, identify the shear center and calculate the necessary values yourself with MATLAB program. So, the whole intention of this course is to make you independent researcher, an independent thinker, and not making you dependent on using software as a black box. So, advancement is not only on design process, is not only on defining equations, not only on checking stabilities, not only on understanding plastic design, it also enables you inherently to be an independent thinker. So, the MATLAB program is not that difficult, it is a very user friendly software. You have got good support from MATLAB Incorporation. So, they will try to help you answer your queries on time, and you can also contact me through discussion forum, but the whole objective is try to learn, have a grip of the problem and enjoy your creation as a programmer. Okay, that is the beauty in the whole exercise, right. Having said this, let us do a couple of more problems. So, now I am going to take a different section. I will call this as example 3. So, I am going to use or check an unsymmetric section, friends. This is a very tricky problem. So far we have been discussing the shear center location for a symmetric section. The section at least had one axis of symmetry, the shear center was located along that axis. But that is not the truth all the time. You can have unsymmetric sections. Unsymmetric sections have their own complications. I think we all know that now by this time we have understood how to operate an unsymmetric section. Let us take an example. I have a section like this, unequal channel section with unequal flanges. Let us mark the dimensions of the section. Let us say this is 40, this is also 40, and this is 20. The section has uniform thickness of 2, all dimensions are in millimeters. Okay. So, the moment I have an unsymmetric section, I will mark the axis, the z and y axis, x axis normal to the screen, this is my y axis, this is my z axis. So, immediately these values are required. I call this as z bar and I will call this as y bar. This may CG, not the shear center, it is a CG. Okay. We will divide this as 3 parts. This is part number 1, component 2 and component 3. Can you find the z bar and y bar? Now, to locate CG is the first issue here. That is, I want to find z bar and y bar of this problem. We know z bar is given by the simple expression algebraic sum of a z bar by c and y bar is a y bar by a. We know this. Okay. So, let us work out z bar. So, 20 into 2 into 10 plus, this is for piece number 1, 40 into 2, 40 into 2 into 20, this is for piece number 3 plus 36 into 2 into 1 piece number 2 divided by 20 into 2 plus 40 into 2 plus 36 into 2, which will give me z bar as 10.8 mm. I mark this value. Okay. Let me copy this figure. Let us find y bar. H can be 20 into 2 into 1 piece number 1 plus 40 into 2 into 39 piece number 3 plus 36 into 2 into 18 plus 2. Am I right? This is for piece number 2 divided by 20 into 2 plus 40 into 2 plus 36 into 2, which will give me y bar as 23.96 millimeters. So, let me mark this value as 23.96. Okay. I also want to find the moment of inertia of this section, because I want to locate the principal axis in the unsymmetric section, is it not? So, the next step will be step number 2, to find Iy and Iz, and of course Iyz for this section. Then only I can locate the principal axis. Okay. I can write Iz directly here. Z is the horizontal axis. I can use parallel axis theorem. So, 20 into 2 cube by 12 plus 20 into 2 into 22.96 square. This is for piece number 1 plus, okay, let me do it, plus 40 into 2 cube by 12, 40 into 2, 39 minus 23.96, the whole square, am I right? Okay. This is for piece number 3 plus 236 cube by 12 plus 36 into 2 into 23.96 minus 20, the whole square. This is for piece number 2. If I do this, I will get this value as 4.8 10 power 4, which is Iz. Okay, let us copy this figure. Let us do Iy. Iy is a vertical axis, which will be 2 into 20 cube by 12 plus 20 into 2 into 10.8 minus 10, the whole square. This is for piece number 1 plus 2 into 40 cube by 12 plus 40 into 2 into 20 minus 10.8, the whole square. This is for piece number 3 plus 36 into 2 cube by 12 plus 36 into 2 into 10.8 minus 1, the whole square. This is for piece number 2. So, if I do this, I will get Iy as 2.57 10 power 4 mm4, which is Iy. Okay, friends. This first principles, I mean there is no confusion in this, very clear. We have used parallel axis theorem, we have done it. Okay. Let us do Izy. Izy is 20 into 2 into 0.8 into 22.96. Very simple. You can see this value, this will be here, and for the first piece, see this value, this will be here. Okay, this is for the first piece, plus 40 into 2 to minus 9.2 into minus 15.04. You can very well see this CG is located here. So, it is negative in terms of y, it is negative in terms of z. Okay, and these values can be seen from here. This value is this, and this value is this. Okay, plus this for piece number 3, plus 36 into 2 into 9.8 into 3.96. This is for piece number 2. This is 10.8, friends. Make a correction here, I am sorry. So, this value is same as this, and this is 3.96, it is coming here. So, Izy after you compute will become 1.46 10 power 4. Since Izy is not 0, the section will be now subjected to unsymmetric bending, and z and y will not be the principal planes. Okay, we know that. So, once we understand this, I can straightaway locate the angle of inclination of this figure. Let me draw this figure again. And let us mark the UU axis and VV axis. So, this is my V, this is my U axis, and we know this angle measured from positive Z is alpha. Okay, and we know tan 2 alpha is given by minus of IYZ by Z minus Y. Now, we have all the 3 values with us. We will substitute them, minus twice of 1.46 10 power 4 by Z value is 4.8 and Y value is 2.57. Okay. So, we get alpha as minus 26.31 degrees measured clockwise from positive Z to positive U. So, this is 26.31 degrees. So, I have located the principal axis. That means job is going to find out IU and IV, because I need to find IU, the moment of inertia about the principal axis now. Okay. So, we know IU is IY plus iz by 2 plus z minus y by 2 cos 2 alpha minus iyz sin 2 alpha. This equation we already derived, we know. So, substitute them, we will be getting 64144.83 mm4. IV can be also said as Iz plus Iy minus Iu. So, I can say 9645.17 mm4. You can check these values, friends. Okay. Once we obtain this, our job is to locate the shear center. Let us draw this figure again. Okay. So, what I am now going to do is, okay, I will redraw this figure slightly. Gentle, okay, angle. Alpha is 26.31. Okay. So, now if I remove this label and say I am going to apply the load V and the reaction VR here along the UU axis. Please understand, I am writing it normal. So, it is along VV axis. So, let us say this is V. This is the principal axis. Okay. So, I call this as VR. Now, if I take moment about this point and I call this distance as E, I have an advantage. If I write this as V1, V2 and V3 and I call this point as A, by taking moment about A, V2 and V3 being concurrent about A will cause no moment. So, I do not have to work out V2 and V3. So, V2 and V3 need not be calculated. So, I want to calculate only V1. So, to do that, I will cut a section. Okay. This section will be at a distance Z, thickness dz, and the CG of this need to be measured from this axis. Okay, I want this CG. Remember that. Okay, we want this. We call this V bar, am I right? because I am transforming everything into the principal axis now. So, now to find V1. V1 is tau dA integral, which is integral tau dz of t. So, tau is VA y bar by IT, which is VA, now V bar by IU into T. Am I right? Please look into this equation. I am transforming them into principal planes, right. Therefore, V1 will be V by IU integral A V bar by T into T dz, which will be V by IU ZT into V bar by T into V bar dz, because this T goes away, right. Okay. So, now I want to find this V bar. This V bar is now equal to, we can make use of this figure. If I have two axes, y and z, if I have another two axes, v and u, and this angle is alpha, in simple terms v can be given by minus z sin alpha plus y cos alpha, is it not? So, I want to substitute the z value minus of minus 20 minus 10.8 minus z by 2 sin alpha, which is minus 26.31 degree, okay, plus 22.9 cos alpha, which is minus 26.31 degrees. So, friends, we have the V value with us, which can be simplified and said as minus of 9.2 minus z by 2. Okay, this is z. Okay, let me make it very clear. Minus z by 2 of minus 0.44 plus 20.5. Okay. So, V now becomes, or V bar, okay, becomes minus 4.048 plus 0.22 z plus 20.93. which becomes 16.482 plus 0.22 z, right. So, once we have this value, I can substitute in V1. I will leave a small homework here. I want you to do this before you check this result. for my next lecture. So, in this lecture we learned how to work out shear center for asymmetric sections. Okay. I also left you a homework exercise and you will check that before you attempt to the next lecture. Thank you very much and have a good day.